Okay. Hi, everybody. This lecture is a continuation to the previous one. The previous lecture was number 13. In the previous lecture, I have introduced to you the sklearn library and the data sets which are there included. We have downloaded two of them, Load Iris and Fetch California Housing. After we have loaded the data sets, we have examined the general description of each by using the description function. We have found the shape of the data frame which was derived from the bunch. Remember, the sklearn gives a data structure called a bunch. The bunch has some definite attributes like data and feature names, target names, frame, and description, DSCRB. You can call the attributes by using the dot notation. By using the dot notation with the as frame, we can convert the bunch to a pandas data frame. After that, we have examined the existence of missed values or zero values in some of the rows for each of the features. And we have used there also the sum function so that the total number of positions where we have zero values will be counted. Fortunately, we did not find any zero value. After that, we also divided or splitted the data frame to the major two parts which are required by regression functions. The first part, which is a data frame of the features, which includes a given number of rows and the number of columns equal the number of features. And the second part, which is a pandas series, which includes the data target, the data frame target. We denoted the features by capital X and the target by small y. Yeah. After that, we use the correlation function to find the correlation coefficients between each of the features and the other feature, and also to find the correlation between each of the features and the target. This was necessary to define the most influential features. Regarding the Fitch California housing dataset, we found that the most important features are 2, and so we neglected the other features. The total features were 8. We only used 2 with 1 target in order to carry out linear regression. We have also established a matrix of the correlation coefficients so that we can see easily these correlation coefficients. And the last thing we have done, we have scaled the values of the features by using a specific standardization method. This was necessary so that to keep the range of change of each of the features close to the other features. This is important for regression to converge easily and to give a high goodness value or a very small mean square error, and to diverge and to converge easily and quickly. I think this was the last thing which we have done. Today we shall continue with the same example with the dataset Fitch California housing. So now we have the features scaled, and they are given a name X scaled, as you see here. We did not scale the target because it was only 1 target and there is no error of that. No need for that. There is not a lot of targets so that to make their range very close to each other. Okay. So at the beginning, as usual, from the sklearn library, we call the model selection model selection, and import from there a function called train test split. This function is very important and used in every activity of sklearn for regression purposes because it splits the whole data set to 2 parts, a training part and a testing part. Testing part will have a smaller size. Usually it is about 20 to 25 to 30% of the whole data set. And the training part is usually about 60, 70, 65% of the whole data set. So by this now we shall have a training X value, X training and Y training, and we shall have X values for testing and Y values for testing. Now we shall call the linear regression method also from the linear model of sklearn. Note that the linear regression is written by big letter, capital letter L and capital letter R. linear regression. In order to evaluate the performance of the process, of the regression process, we shall use two criteria. One of them is the mean square error. So we imported the mean squared error function and also the R squared score function. So we have imported both, and we shall use both to have an indication about the goodness of the regression. And I think we have talked about that before. We are going to rely mostly on the mean square error and to make use also of the R squared score. Okay, so as we have imported the train test split function, now we use it. Train test split function is called now between two brackets. This means that we are calling this function, and we will pass there the necessary arguments. The first argument is the X trained, and it is already scaled. We call it X scaled. So here we will put X scaled. And this is why. Why we did not scale it, as I told you. Here we define the test size, or the portion, the size of the testing elements will be about 20%, 0.2. And in order to guarantee repeatability when we run the program, we use a random state equal to 45. So as a result of that, now we shall get X train, X test, and Y train, Y test values. Each of them is an array. So in order to work on the data sets here, we initialize the regression function, linear regression, between brackets here, and we assign it to an object variable. We call it model. Some people call it regressor also. And this model now is fit to the data which we have, X train and Y train. Here is the process of reading the data set happens by the model. And as a result of that, we can now find the required output characteristic values for regression, such as the slope of the linear regression. It is called coefficient underscore here. So we print model dot coefficient underscore, and the same thing applies for the intercept value, model dot intercept underscore. So now we can get the values directly calculated by the model. In order to test the model and that it works perfectly without training, with a value, with a data frame which is not included in the training process, which is the X test and Y test. So we apply the model to predict the values of the X test portion. And the model now will give us an output, which is the Y predicted values. I have printed a sample of the predicted values for the rows beginning from 0 to 7. Now we shall see it. Also, now I want to evaluate the performance of the regressor. So I called R squared score and function, and I passed there the Y test and the Y predicted value. And I get now the R squared, which is the output. This value usually, if we have a very good work, it is about 1. This is the best performance. If it is very close to 0, this means the performance is not good, and we have to modify something or to do something with the data set. Also, we have called the mean squared error function, and also pass there the same values, Y test and Y predict, in order to have the mean square error value. And here the mean square error value gives also another information regarding the goodness of the regression. And as this value is small and very close to 0, this means that the regression process was carried out perfectly. If it is around 0 and small enough, it is accepted. But if it is high enough, so this means that it is not good work. So if we go down and look at the results which we have in our work here, so yes, we are here. This is the array of the features. We have only 2 features. We have selected in the previous lecture 2 features, the median income, and the average number of rooms. We have taken this feature and this feature as the most important here. I have defined their values for only 3 rows. And this is the values, these are the values of the target for the first 3 rows also. The X value here, this array, which is, as you see, 2-dimensional, is scaled. We have scaled it, and these are the values after scaling, and you can see that the values really are very small, 1 to about 1, about 0, 1, 0. The range is not that high, which is required by regression algorithm. Now, after we applied the regression to the function, to the data set, we found the coefficients. We have only here 2 features, so we have 2 slopes. This is the value of one slope, and this is the value of the other slope. The intercept is common for both. It is given this value. Predicted first 7 values, as I showed you up, here they are given just as an information to be sure that there is the function working and giving results. The value of the R squared here is, as you see, 0.46. It is about half. This value generally is acceptable when working with regression functions. It is not very close to 1, but it is acceptable. It doesn't show a serious drawback or malfunction. The median square error also, as you see here, 0.7, which is close to 0. And this is also a good result. So we can say that the regressor works normally. So now we have found these values and we want to carry out the regression activity, but not by using the linear regression function of sklearn. We want to do that by using OLS, or in other words, ordinary least square method. We have done this before, but here really I am interested to do it for you again so that we can compare between the results. But you remember when we worked with the OLS method, we need always to add a constant to the training set. So here, first of all, we have called previously the stats model as SM. From stats model SM, we add constant of the X training, and we call it the same thing, X train, and add to that underscore SM. X train underscore SM is the X train with added constant. Having this with us now, we can apply the model SM OLS. This is the regression function here, OLS between brackets, and we pass the arguments, which are Y train and X train SM. X train SM because we have added the constant. And after that, we also use the fit function to fit the model to the data set. So all the work here is done, and now this S model can give me the information related to the regression operation. We do that by calling summary model SM dot summary function, and this summary function contains, it is a table as usual, and contains the information related to the regression process. So as usual, you can have a look at and compare the results with the linear regression of sklearn. As you see, the R squared there is 0.48. There it was about 0.46. They are very close, no difference at all. You can also see the intercept value 2.067. Here it is about the same thing, 2.0677. It is the same value. The inclination or the slope of the first linear regression line is 0.82. Here it is 0.82, the same thing. And the other one is minus 0.9, minus 0.99. So as you see, we have exactly the same results. This is good to apply in real life so that you can compare between results and be sure that the results are real and there is nothing wrong with it. Okay, so now we have carried out the regression process, but as usual, we need always to plot the line of regression or the scatter plot, which represents the results of predictions and the initial data set, so that we can judge about the performance also by eye, by using our eyes. Yes. Okay, so let us do that. For doing that, firstly, I have again shown you that we have defined the two features which were selected and will be used for regression. Here they are, and they are called columns to plot because we want to plot them. Before plotting, of course, we have to configure a figure object using PLT from Matplotlib. So we have defined the figure with a size. And now we want to plot a scatter plot to compare the positions of the predicted values with the positions of the initial values which we have. So PLT scatter plot, we open the bracket here and pass the necessary value, X and Y. X here, we use X test, but for testing, you remember we have two variables, two features here in X. We here are using the first one. You can use 0 to 1 because we have only selected two features. You can use here semicolon apostrophe 1 or semicolon 0. So we pass here X test of 1, Y test, we give it the color red, and a label because it is X test and Y test, it is the real value, it is the actual data which we have, the initial value which we have, the original value. And now we plot the predicted values. So instead of Y test, now we use Y predicted. We give it a color yellow, and we label it by predicted data. So as you imagine or expect here, we shall have two scatter plots overlaid on each other in order to see by eye how close or how far they are from each other. If we look at the result here, we see this figure, this plot. The red dots here represent the values, the actual values, and the yellow represent the predicted values. And as you see really here, mostly the yellow values are overlapping with the red values. And in some cases here, as you see, with these outliers, they are also close to them, not so far from them. But of course, such a value here and this value here are outliers and may not be considered. You can imagine from 20,000, for example, values, 20,640, that these two values do not exist close to each other. There is no problem with it. But such a plot here shows you that the real convergence happens and the real work is okay and the result is acceptable. Also, in addition to this figure here, usually when we have a number of features, it is very necessary to carry out some exploratory work so that you know how each feature was oriented relative to another feature, how they are correlated to each other. This is usually done by using the pair plot function of sklearn. sklearn, as I told you, is a plotting library built on the top of Python. It is imported at the beginning of this program and abbreviated as SNS. So here from SNS, from sklearn, we imported pair plot and passed to this function the data frame. It is called here df4. I have generated a new layer specifically so that to work with it alone, so that to be clear for you. And now, if I look what happens, here we have a pair plot. Every feature will be plotted relative to the other feature. So if we have two features, we shall have 4 plots. 2 by 2, we shall have 4 plots. If we have 5 features, we shall have 25 plots. In our case, we have 8 features and we have 1 target. So the total is 9. So we shall have 81 plots, with each of them represents the relationship between 2 definite features. Let us look what we have received. Here they are. Now, this is the median income. This is the house age. This is the number of rooms. This is the average bedrooms. This is the population. This is the occupation, and so on. They should be 8 with 1 target. 1, 2, 3, 4, 5, 6, 7, 8. And this is the target, which is the median house value. We arrange them. They are arranged by the program horizontally and vertically with the same inverse order. Here is the last one, the median house value. Here it is. Now this is the longitude. Now here it is the longitude. And this is the latitude. Here is the latitude. And you go up to the moment when you come to the median income. Here, medium income at the beginning. Now we have here 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 by 9 will be 81 plots. Each plot of them represents how every 2 features related to each other. If we take, for example, this feature here, it represents the house age relative to the latitude. If you come here and see, this is the population related to the longitude, and so on. What is the importance? The importance it gives you in advance a picture of how the features are related to each other, and also the most important, how the outliers, such these points, and how they are, what is the number and the total of them relative to the whole number. As you see in most of the cases which we have here, the points here are always concentrated very close to each other, and the outlier values are very limited, which means this is a good thing. Also, I have plotted for you only two plots between the median, the mid-income, and the median house value, and the house age and the median house value. Why? Because I am interested only with these two features. As I told you before, we are not interested with the whole picture. I have plotted them separately here. If we go up and see, we have used the same function, of course, per plot function, but the input there will be the, yes. So now we have defined the features, and this is called a column to plot, and where it is, here they are. So we used S and S per plot. This is the function name. This is the features to use. And this is the output or the target to use. These two variables are compared with this variable separately to give a specific picture only for the features under consideration. What is also interesting here, as I told you just before, we have, or I have again created a data frame representing the data set, and it was given a DF4, data frame number 4. Very often it is very useful to overlay the line of regression or the regression line over the scatter plot. To do that, we have, of course, to use the pair plot at first so that we can have the scatter plot. So through the SNS, we call the pair plot. We call there the data which we have, DF4. And now, in order to overlay the regression line, we include here an argument called kind, and here we define what we mean by this argument, regression. So between two brackets, two primes here, we write reg. This argument means that we are asking the pair plot to overlay the regression result on the scatter plot. One thing also interesting, the dialog kind is KDE. What does it mean? What do we mean by dialog and KDE? KDE, kernel density estimate. If we go back to the picture which we have here, we shall have a diagonal where we have a histogram which represents the distribution of the values, discrete values of the feature, of this feature, or this feature, or this feature, and so on. This is a histogram type in the diagonal. This gives you an idea how the density of the feature is plotted as histogram bins. Sometimes you do not need or you do not like to have it shown discretely as it is shown here in a discrete shape, and you want it to be in a way or another as an analog, as a curve. Here it is. Here now I have defined the pair plot for the two features with the regression line overlaid on each, and the diagonal here is in a KDE mode or shape. It is continuous and not consisting of bins as it is in any histogram. The use of this figure, as you see, it shows you the distribution of the values of the median, of the median, yes, income, for example, relative to the, here it is, median income. And it shows you how it is it normally distributed or somehow skewed? It is really here accepted distribution, but it is skewed, as you see here. And in this figure here, it is not skewed that much, but it is not exactly a normal distribution. It is distorted normal distribution figure. This information are necessary also and could be used by you when working on further tasks, another tasks related to the work which you are doing now. So at the end now we have finished with this example. We have carried out linear regression process by using sklearn linear regression function and by using ordinary least squares method. We have carried out regression only for two features and found the intercept and the slope coefficients. We have also plotted the scatter plots of all the features and the scatter plots of selected features. And we have also overlaid the regression line on the scatter plots, which is of importance, of course. Yes. And at the end, we have changed the nature or the type of the diagonal shape, which represents the probability distribution of the values from histogram to KDE model. I think this is the target of this lecture. Now, this lecture must be read with the previous one together so that you can understand and relate values and concepts relative to each other. Okay, finishing with this today. I wish you the best and see you in the coming lecture. Goodbye.